Welcome back now to our discussion on orthogonal complements. We continue still our conversation concerning orthogonal complements by discussing what your textbook calls the fundamental subspaces of a matrix. We'll discuss these subspaces and the relationships between them. So for this entire conversation, we'll fix an M by N matrix A. Then there are four subspaces that we're concerned with now. Let's list them. First, we have the row space of A. This is the vector space or the subspace of A, which is spanned by the rows of A. Next, we have the column space of A. That's the subspace which is spanned by the column vectors of A. Next, we have the null space of A, and that's the collection of all vectors that are solutions of the homogeneous equation with A as a coefficient matrix. And finally, we have the null space of the transpose of A, which is, of course, defined similarly, but using the transpose of A. It's good to keep track of which vector spaces these various fundamental subspaces are subspaces of. For example, the row space of A consists of the span of the row vectors of A. Those row vectors have n components, where n is the number of columns of A, so the row space of A is a subspace of Rn. The column space, on the other hand, is a subspace of Rm. The null space of A is again a subspace of Rn. And finally, the null space of A transpose is a subspace of Rm. Perhaps we can do an example right now, a small example, easy to calculate, where we calculate all of these subspaces for a matrix A. I guess before we do though, let's also comment that we have some names for the dimensions of some of these subspaces. Recall that the dimension of the row space and the column space is the rank of the matrix. The dimension of the null space of A is the nullity of the matrix. And it's an exercise, if you haven't done it, it's an exercise now, that the dimension of the null space of A transpose is also the nullity. So let's record that information. Here I've written the rank of A is the dimension of the subspace occurring in 1 and 2. And the nullity of A is the dimension of the subspace occurring in 3 and 4. Here's our example we'll work on for a few minutes. A is the following 3-row by 4-column matrix. For this matrix A, we'll calculate the row space, the column space, the null space, and the null space of the transpose. So, to begin, the row space, well, I mean, the row space is sort of staring right at us. We can just simply define the row space as the span of the row vectors, so we'll write that down. So I've written down the row space. It's the span of the row vectors, where I've taken each row vector, this one, and this one, and simply written them as column vectors in this spanning set. But we can do a little better. This set may or may not be a basis for the row space, so let's see if we can find a basis. Remember, we have two methods of doing this. One method will yield a basis which is a subset of the original rows, and one method will yield a basis which is not necessarily a subset of the original rows. Let's use the second method, or the first method, which will yield a basis which is a subset of these rows. So to do that, we'll take A and write down its transpose, and then take the transpose to RREF. So when we take this matrix, here's the transpose of A. Rows go to columns, and when we take the RREF of this matrix, we get the following. So we find that we have pivots here, here, and here, which means a basis consists of this vector, and this vector, which in the original matrix is this vector, and this vector. So the conclusion here is that these three rows are linearly independent and therefore are a basis for the row space of A. Of course, since the rows of A are vectors with 4 components, they live in R4, so we conclude that the row space of A is a three-dimensional subspace of R4. Now let's go on and calculate a basis for the column space. Of course, it's easy, again, to write down the column space of A. We simply write down the column space as the span of the 4 columns of A right here. But again, we can do better. We could write down a basis for the column space. We know in this case that a basis for the column space can't consist of all 4 of these vectors. We know that because above we found that the row space had a basis with size 3, that is, it was three-dimensional. That's the rank of the matrix, and of course the rank of the matrix is both the dimension of the row space and the dimension of the column space. So since we calculated this row space explicitly above, we know this is 3, and therefore this thing must be 3 as well. So the column space has dimension 3, so any basis must have 3 vectors. The column space here is spanned by 4 vectors, so this cannot be a linearly independent set. Of course, we know for a completely different reason that this set can't be linearly independent, because these vectors are vectors which lie in R3. And so the space that they span has to be a subspace of R3. And R3 only has subspaces of dimensions 0, 1, 2, or 3. Now, of course, R3 has no 4-dimensional subspace. So that's another more basic reason why these things can't be linearly independent. So anyway, let's try to find a basis. Again, we can try to find a basis consisting of some subset of these vectors, and we're expecting to find 3 vectors in a basis. So we'll employ the technique we used above. We'll take the matrix A and we'll take it to RREF and pick out basis vectors in that fashion. So here we go. We find that the RREF of this matrix is the following matrix, and so now we go through and we just pick out the pivot columns. We have pivot column, and pivot column, and therefore a basis for the column space of A is obtained by taking the first, second, and fourth columns of the original matrix, which is this set here. So again, note this is a subspace of what, R3? Well, since it's three-dimensional, in fact, the column space is all of R3. That's the only three-dimensional subspace of R3. And of course, as we expected, the dimension of the column space here is equal to the dimension of the row space we found above, even though they live in different spaces. Now let's go on. The next fundamental subspace we need to find is the null space of A. Of course, remember, we find the null space of A by solving the corresponding homogeneous system, which is this thing right here, and we'll solve this by taking this thing down to RREF. We actually did that above when we solved for the column space of A, so we don't need to do that over again. So we obtain the following. There's that RREF. If I denote my variables by Q, R, S, and T for this system, then I see I have pivots here, here, and here. So if I rewrite that in terms of Q, R, S, and T in linear equations, I obtain T equals 0, R equals negative S from the second row, and Q equals 2S from the first row. So we can write this as a basis set. So a vector in our null space looks like QRST, and now we invoke the relations we obtained above from solving for the null space, and we get, well, because we had one free variable above, we have one basis vector. It's this one right here. So the null space is the span of this single vector. Therefore, the null space is one-dimensional, but we should have been able to conclude that even before we calculated the null space explicitly. After all, one of the main theorems from the previous section on rank told us that the rank plus the nullity of a matrix is equal to the number of columns, or n. Rank plus nullity equals n. That's 4 in this case. A is a 3 by 4 matrix. So the nullity must be solving for nullity. The nullity must be 4 minus the rank. We calculated the rank above.